lesson, we looked at possible ways for the physical implementation of a qubit based on a number of quantum systems. Let us now discuss the notion of qubit not from a physical, but from an informational point of view. To do this, we compare the qubit with a classical bit and show what their similarities or differences are. It is well known that the unit of information quantity in classical calculations is a bit. One bit can take only one of two values, which are usually denoted as 0 and 1. In this respect, a bit is similar to a coin. If a coin is perfect, it cannot stand on an edge, then when it is tossed up, either a head or a tail will drop out. Thus, if a certain physical object can take only one of two possible values, then a bit of information is required to describe such an object. If the object is able to accept m values, then its description will require binary logarithm of m of classical bits. For example, to describe the color of the traffic light signal, you need to use 2 bits of information. Green can be described as 0, 0, yellow is 0, 1, and red is 1, 0. The value of 1, 1 will be superfluous. A qubit is analogous to the bit in a quantum computing. The qubit also has 2 basic states, which are denoted as 0 and 1. These states are seen the values of the 0 and 1 classical bits. However, as we found out, in contrast to a bit, a qubit can also exist in various intermediate states, that is, be in a superposition of states 0 and 1. Therefore, in a general case, its state can be represented as a linear combination of state 0 and state 1, with complex alpha and beta coefficients. In the examples, with a coin and the traffic light, each value of the classic bit carries certain information about the state of the object. In this case, with the help of the 1 bit, 2 states of the object can be described. With the help of 2 bits, we can describe 4 objects, and so on. In this regard, a natural question arises: how many different states can be described using a single qubit, which in general is a superposition of states 0 and 1? To answer it, we'll give one simple but very useful geometric qubit interpretation. So, to obtain the geometric interpretation we need, let's consider the qubit state psi in general. So, ket psi equals to alpha state 0 plus beta state 1. Here, alpha and beta are complex numbers, and it's well known that any complex number could be described with pair of 2 real numbers. So let the alpha equals a e to the power I psi, and beta equals b e I phi. And here a, b, psi, and phi are real numbers. These numbers obey to normalization conditions, and we can write the following expression: alpha squared plus beta squared is equal to. So let's again rewrite the state vector psi in accordance to normalizations. Psi equals to cosine theta in half e power to I psi in the state 0 plus sine theta in half e powered I phi on the state 1. Here cosine of the theta in half and sine of the theta in half is just numbers a and b. So let's take out the phase factor e powered I psi. e powered ixi on the cosine theta in half on the state 0 plus sine theta in half multiplied by state I gamma, whereas gamma equals phi minus xi on the state 1. So here the phase factor e powered ixi, we can just take it out. So it's an arbitrary phase factor, and finally we get the following expression: cosine theta in half on the state 0 plus sine theta in half on the state e powered I gamma on the state 1. So as a result, we obtain that qubit state psi is dependent on two real numbers. It's theta and gamma, and that will help us to get the interpretation, the geometric interpretation we need. Thus, to set the state of a qubit, you only need two real numbers, theta and phi. This allows us to represent the state of the psi qubit as a vector, the end of which runs along a sphere of unit radius. This sphere is usually called the Bloch sphere, and in the case when the qubit is realized on the basis of polarized photons, it also called the Poincare sphere. In the picture that you see on the slide, the red arrow indicates the state vector of the qubit psi. The polar angle theta is counted from the z-axis in the directions of the psi state vector and takes values from 0 to 2 pi. The azimuth angle phi is counted from the x-axis in the direction of the projection of the state vector psi on the xy plane and also take a value from 0 to 2 pi. Now, there's a Bloch sphere constructed in the special coordinate system. First of all, as the positive direction of the axis, one can choose the direction of the base vector 0, and as negative direction of the z-axis, the direction of the base vector 1. According to the expression we considered earlier, the vector psi, that is the state of the qubit, coincides with the vector 0 at the theta angle equals to 0, and the psi vector coincides with the vector 1 as the theta angle equals to pi. An angle phi can be arbitrary, and for definiteness it is sometimes taken to be 0. Secondly, the direction of the vector plus is usually chosen as the positive direction of the x-axis. That is, vector plus is the sum of the vectors 0 and 1 taken with a normalization factor 1 divided by the square root of 2. And the vector minus equals to the difference of the basis vector is associated with the negative direction. According to our formula, the psi vector coincides with the vector plus when the theta angle is equal to pi in half and the phi angle is equal to 0. If the angle theta is equal to pi in half and the angle phi is equal to pi, then psi vector will be aligned with the vector minus. Finally, as the positive direction of the y-axis, we choose the direction of the vector plus I equal to the sum of vector 0 and vector 1 multiplied by the complex unit, taken with a normalization factor 1 divided by the square root of 2. And the negative direction of the y-axis is chosen as vector direction minus y, that is, differences of these vectors. According to our formula, the direction of the vector plus I corresponds to the angle theta equal to pi in half and the angle phi equal to pi in half, and respectively to the direction of the vector minus I corresponds to the angle theta equal to pi in half and the angle phi equal to 3 pi in half. Each of the introduced axes of the Bloch sphere has a certain physical interpretation related to the nature of the system under consideration. In the case when the qubit is realized with the help of the spin of atoms, the directions of this axis are associated with the direction of the spin. In the case when qubits are realized using polarized photons, these directions correspond to the types of polarization of photons. For example, the direction of horizontal linear polarization is chosen as a positive direction of the z-axis, and the directions of the vertical linear polarization is chosen as a negative direction. The x-axis is also associated with linear polarization, but already in the basis rotated by 45 degrees relative to the basis for the z-axis. And the y-axis is already associated with the circular polarizations of the photon. We emphasize that regardless of the nature of the physical system under consideration, orthogonal ket factors on the Bloch sphere look in the opposite directions. As we can see, each pair of values of theta and phi angles corresponds to some directions of the psi vector, that is, some quantum states of the qubit. Thus, since the number of points on the sphere is infinite from the geometrical point of view, the number of different states in which one qubit can exist is also infinite. If we could experimentally distinguish individual states of a qubit, that is, specific values of theta and phi angles, that with just one qubit we will be able to encode any letter of any existing alphabet. For example, in order to transfer any lowercase letter of the Cyrillic alphabet with the help of single qubit, we would need 33 different states of it. For example, this is done on the slide. For comparison, we recall that the encoding of every lowercase Cyrillic letters requires 6 ordinary bits of information. In this regard, the potential of the qubit for storing information is not limited. If it was possible to distinguish any intermediate values of the theta angle and phi angle, using a single qubit, it would be possible to encode not only letters, symbols, but even the words. In this case, one qubit would be enough to encode all the words of some existing language. This means that the number of different superpositions, that is, qubit states, is infinite. However, in practice, we can distinguish only 2 states of the qubit. If we measure our qubit in the state basis 0, 1, then with probability squared cosine theta in half, we get the qubit in the state 0, and with probability sine squared sine theta in half, it is state 1. Thus, the reduction of the wave function during measurement allows us to obtain only a bit of information from the qubit state. It is interesting, however, that if the physical system is closed, that its evolution occurs in a unitary way, that is, the position of the end of the state vector on the Bloch sphere described by continuous smooth trajectory. In other words, nature watches all the values of the theta and phi angles at an arbitrary point in time. This information about the evolution of a qubit is quantum, and this information increases with an increasing dimension of the physical system, that is, with an increasing number of qubits. And global information about the states of all qubits allow us to carry out logical operations that are interested from a practical point of view. We'll consider this in the example of quantum algorithms. But before that, we will talk about the nature of the information associated with a phenomenon unique to quantum system, namely quantum entanglement, that is, correlations that occur between separate parts of the composite quantum system, which may consist, for example, of several qubits. In this regard, next time we will start talking about composite quantum systems and the quantum states of such system. And now that's all. Thank you for your attention.